Okay, a couple of things. We're going to talk a little bit about collision theory. So let's hit this. So the first thing we need to know, activation energy is the amount of energy required by the reactants necessary for a reaction to occur. So for gaseous and aqueous reactants, if we increase their concentrations, we're going to increase our rate of reaction. For solids, if we grind them into smaller particles, we'll increase the rate of reaction because we have more surface area. If you think about it, if you do just like a sugar cube, it doesn't react as quickly as granular sugar. And the finer that sugar is, the faster it dissolves. Um, and then stirring will increase the reaction rate in heterogeneous mixtures. Not homogeneous mixtures, because then when we stir it, if it's heterogeneous, if it's all settled to the bottom, by stirring it, we're increasing the rate that those molecules are going to collide. And temperature increases reaction rate because it makes the molecules move faster. Okay, so if we look at this graph, then we have 3 different samples at 3 different temperatures. The green one is the warmest temperature, medium. Since we don't have exact numbers, I am using hot, warm, or hot, medium, and cold. Okay, so the across the bottom is the speed or velocity of the atoms or the molecules. And then across the top is what percentage of the molecules are at those different speeds. I think we looked at these similar a couple of weeks ago for something else. So if we had an activation energy of 5, then if we look at the one that's at the warmest temperature, most of its molecules are beyond that point. If we look at the red, it's got a few, it's got some, it's got more than the blue. So the blue one looks like it's not going to occur at all, and the red will occur very slowly. Another issue with the molecules don't have to just um, collide, they have to collide in the right orientation. If we look at the first one, so these two here collide. So these two are going to break apart, but then that's the only thing that's going to break apart. So it's going to go back to, those two will come off, and you'll wind up basically with exactly what we had started with. And the other one, so if we had a blue, the blue colliding right here, then again, you're going to wind up with basically exactly what you started with. However, if the blue one collides to the side, then it's going to take this one as opposed to, it's going to take this one as opposed to knocking that one off, which is what happens up here. It takes this one. So down here, we wind up with our new molecules. So we have to worry about orientation as well. Okay, mechanisms for reactions. Okay, if we had this equation right here, we normally write our equations in our net reaction. However, most reactions happen in steps. And we saw this when we did the chameleon reaction. You saw the different colors, and those different colors represented the different steps in that reaction. So in this case, these are the steps, and the intermediate forms in one step and is consumed in the next step. So our intermediates in this one is HI. We don't see HI in the final uh, equation, but it's in one of the intermediates. So that is an intermediate form. And if you get rid of your intermediate forms, then you wind up with the equation. Okay, so rate law for the elementary steps. If we start with a single reactant and wind up with products, then the rate, it's a unimolecular step, and the rate is K to the concentration of A. If we start out with A plus B and wind up with products, it's called bimolecular, and we have K to the concentration of A times the concentration of B. If we have A plus A, then again, it is still bimolecular, but we wind up with rate times K to the A squared, which is the same as saying A times A. Termolecular, because the odds of getting 3 molecules to interact at the same time is very slim, is a very rare reaction, but those are listed. I do not believe we have to worry about these much at all, other than to know that they do occur. Okay, so rate determining state. It is usually the one step that is slower than the other. Um, so nothing can go faster than the slowest one. Um, so it determines the rate of reaction. It cannot occur faster than the rate determining step. The reaction cannot occur faster than the rate determining step. Rate determining state determines the rate law for the overall reaction. So if we look at our rate determining state, then we can get the overall reaction. Okay, so if we look at this, and it tells us slow or fast, and so our slowest one is our rate determining step. And if we look at this particular one, we have 2 yields a product. So K is equal to NO squared according to our chart. And that is what they came up with experimentally. So this is a valid reaction or valid intermediates. Okay, so there's 2 rules. The elementary steps in the mechanism must sum to the overall reaction, and the rate law predicted by the mechanism must be consistent with the experimentally observed rate. So again, if you looked back at that, then what we got from the slow reaction from the rate determining step was the same as what was achieved during experiment. Okay, so let's look at this one. Experimentally, the rate law was determined to be Kn. Okay, so this is the same slide, and we want to look to see, make sure that it is we have the overall equation. So NO2, let's see. So NO3 cancels out here. NO NO2. Okay, and this NO2 cancels out over here. So basically, if you see it on the reactant side and then you see it on the product side, you can cancel it out. So then what you wind up with is NO2 plus CO yields NO plus CO2. And so yes, everything canceled out and we wind up with our net equation. Okay, so one more time. So experimentally, this is what we determined. When we have our second step, or not the first step being our rate determining step, then what's going to happen if we looked at this, then experimentally we want, or I'm sorry, by looking at that, we look at rate 2 is equal to K2 times the concentration of O3 times the concentration of O. O is an intermediate. It's going to disappear at some point. And so we cannot have that as part of our rate. So we need to substitute in for O. So to do this, when you see an equation that looks like this means that it has reached equilibrium and the reaction is going both ways at the same pace. So we need to determine the concentration at O at some point so that we can fill it in here. So if we looked at, and this will be K1 and K to the negative 1. And these are equal. Again, they're going back and forth at the same rate. So those are going to be the same. It just depends on which way you're looking at it. So the first, so K1 times the concentration of O3 is equal to K to the negative 1 O3 and O. I'm sorry, K2 and O. Okay, so we want to fill in for the oxygen. So we're going to move all of this over here. So we have K1 over K to the negative 1 O3 O2 equals O. So now that we have an equivalency for O, we can substitute this into here. So now we have K2 equals, I'm sorry, rate is going to be equal to K2 times the concentration of O3, and then substitute in K1, K to the negative 1, O3, O2. Okay, so then rearrange. These cancel out because they are the same. And we have K2 O3 O3 O2, which equals O3 and then O2 to the negative 1. And this number does match this one. Okay, so that's it for today, and we will have some practice problems coming up soon. Thank you.